Today we will be tackling a classic control problem using this pendulum, but with a very non-traditional approach. We'll show how you can use Agentic AI to go through the entire engineering workflow from defining requirements and designing a controller to simulation, testing, and hardware deployment. This workflow combines model-based design with Agentic AI. If you worked with an AI coding assistant before, you've probably seen it works best iteratively, breaking problems into smaller pieces and tackling them step by step. That's especially important in engineering workflows, where each step must be correct, traceable, and verifiable. It lets you review results as you go and quickly pinpoint where issues need to be fixed. That's exactly what we'll do today. Guide the AI agent through each step of the control design workflow. Along the way, the AI agent will generate MATLAB scripts, Simulink models, and ultimately C code for embedded deployment. All verifiable artifacts you can inspect, use, and refine as needed. Our target system is a Quasar Cube servo rotary inverted pendulum connected to a Raspberry Pi. The goal is to swing the pendulum up from its hanging position and balance it upright. This is a non-trivial control problem for a few reasons. The system is underactuated, meaning we can only apply torque to the arm, not the pendulum directly. It's inherently unstable at the upright position and exhibits strongly nonlinear behavior during the swing-up phase. So we need a swing-up strategy to inject energy into the system, a balancing controller to stabilize the pendulum near the upright position, and a switching logic between the two control modes. On the AI side, we're using Cloud Code as our coding agent. It is connected to MATLAB via the MATLAB MCP core server. On top of that, we're using the MATLAB Agentic Toolkit and Simulink Agentic Toolkit, which give the AI agent the tools and expertise to work directly with MATLAB code and Simulink models and follow proven engineering workflows instead of building everything from scratch. Now that we know how everything is connected, let's dive in. I'm working from a project folder where I've provided the agent with reference models to use in this session. These include the previously developed Simscape model of the rotary pendulum and another model we'll use later for deployment. My first prompt describes the hardware and engineering workflow I want to follow. It also tells the agent how I want it to work with me iteratively so I can review the generated MATLAB scripts and models at each step before moving on. We ask the agent to help define requirements so we have a set of measurable criteria to verify the control system against. It begins by interviewing me to clarify control objectives, performance expectations, and constraints. I specify that the pendulum should start from the hanging down position and balance upright. I also define additional requirements such as settling time, motor input voltage, and a 5 millisecond sample time to ensure the controller can execute reliably in real time on the Raspberry Pi. In addition, we include robustness requirements to account for variations in motor resistance and pendulum damping. With the requirements defined, we explore possible control strategies. The agent proposes energy-based swing-up combined with a stabilizing controller like PID, LQR, or linear MPC, as well as a fully nonlinear MPC approach for the entire task. We rule out nonlinear MPC because it's computationally expensive and may not reliably run on the Raspberry Pi. For our control problem, we will use linear MPC, which allows us to handle voltage constraints. Next, we move on to plant modeling and linearization. Since we already have a Simscape model available, we'll use it as our plant model. However, when you don't already have a plant model available, the AI agent can also create one using the Simulink Agentic Toolkit. In this example, we'll work directly in Simulink, although more complex system architectures would typically also involve System Composer. We prompt the agent to linearize the nonlinear Simscape model and obtain the state space model for use in control design in the next step. The agent starts running simulations with the Simscape model. It then writes MATLAB code that generates validation plots that compare the linearized and Simscape model responses to a step input. The agent also provides a summary showing that the agent used the linearized function from Simulink control design to create the linear model, discretized it with a 5 millisecond sample time, and computed system polls. Next, we ask for an interpretation of the polls along with a pole zero map to visually inspect them. From the plot, we observe an unstable pole in the right half plane, indicating that the upright equilibrium is open loop unstable. This means that once the pendulum is near the upright position, even a small perturbation will cause it to fall without active control. So next, we move on to controller design to stabilize the pendulum. We ask the agent to build a controller model that implements a two-mode approach: a swing-up controller that pumps energy into the system to bring the pendulum near the upright position, and a model predictive controller using Model Predictive Control Toolbox to balance it once upright. We also need switching logic between the two control modes. After prompting, we can watch the agent work step by step to build the controller model, which is pretty cool. Once it's done, the design summary shows the implementation details of the controllers and supporting components. The MPC block uses an MPC object that the agent has already created, which we can inspect in MATLAB. We can even ask the agent to justify its design choices. For example, it explains selecting a prediction horizon of 80 steps or 400 milliseconds to capture at least one full swing of the pendulum. In the model, we can also explore the swing-up controller and the hysteresis-based switching logic, both implemented using MATLAB functions. With the controller model in place, it's time to test it against the Simscape-based plan model using closed-loop simulations. As the agent starts running the simulations, we notice that things don't quite go as planned. The simulation results showed the pendulum swinging up and controller switching to MPC, but it still fails to stabilize. We then ask the agent to investigate the issue. It traces the root cause to the MPC's built-in state estimator, which runs throughout the entire simulation, including the swing-up phase. Because the estimator is based on a linear model that's only valid near the upright position, it diverges during large swings and produces poor state estimates. To address this, the agent proposes bypassing the built-in estimator and directly using the state measurements that are available to us. We go with this approach. Alternatively, we could have designed an extended Kalman filter if all states measurements were not available. With the updated controller, it reruns the simulation and we see the pendulum swing up and successfully balance in the upright position. From the generated plots, we observe repeated large angle swings and increase in the pendulum's velocity and arm angle as energy is injected into the pendulum. Around 3.5 seconds, the pendulum reaches the upright region and the controller switches to MPC, after which the angle and velocity quickly settle near zero. We can also see that the motor voltage remains within the limits of plus minus 12 volts. The agent summary shows which requirements are met during the closed-loop simulation-based testing. Next, we ask the agent to proceed with the robustness analysis. It generates a MATLAB script that varies the parameters in the Simscape plant model, sweeping motor resistance by plus minus 15% and pendulum damping by up to 50%, while keeping the controller unchanged. The MPC controller is still based on the nominal linear model obtained from the Simscape model, allowing us to evaluate how well it handles plant model mismatch across all 25 parameter combinations. The agent then writes MATLAB code that generates a pass-fail heat map, which appears fully green, indicating that the controller meets all requirements for every parameter combination tested. We also see the pendulum trajectories for all simulation runs. Once the pendulum balances upright, all trajectories converge to zero quickly despite the parameter variations. Finally, the nominal versus worst case comparison shows that the worst case scenario requires more swing cycles and reaches the voltage saturation limit during the last swing before stabilizing. The agent also updates the requirements summary table to include the robustness analysis results, where we now see that all requirements passed successfully. Next, we move on to software in the loop or SIL testing. We ask the agent to generate C code from the controller model and run a SIL simulation to verify the generated code produces identical results to normal mode. The agent runs the closed loop simulation in normal mode first. It then generates C code from the controller using embedded coder, compiles it, and runs the simulation in SIL mode. It compares the results from both runs, where we see they match exactly. And because the code is generated with embedded coder, the same model always produces the same code, and every line of code traces back to the original model. The generated code is deterministic, traceable, and certifiable. The last step before we can move on to deployment is processor in the loop, or PIL testing. It is the same concept as SIL, but now the generated code runs on the target processor, Raspberry Pi in this case, instead of the host PC. With the RPI object already available in MATLAB, we prompt the agent and see that it enables execution profiling, sets the controller to PIL mode, and finally runs the PIL simulation. Again, the results are numerically identical to the normal simulation. We can also review the code profiling report, which shows that the generated code passes all feasibility checks with low CPU utilization and execution times well within the required limits. In the final stage, we ask the agent to build the deployment model using the provided reference model for SPI connection with the Cube servo hardware and deploy it to the Raspberry Pi. Our first attempt didn't work as expected, so we went back and forth with the agent to investigate the issue. We eventually identified some mismatch between the model and the hardware, such as signal ordering and sign convention issues, as shown by the open-loop testing results. With the agent's help, we fixed these issues and redeployed the model. Using the provided reference model, the agent connected the Raspberry Pi to the Cube hardware through SPI communication and created the deployment model by integrating it with the controller reference model. It also generated a MATLAB deployment script that can now be reused to deploy the model directly to the hardware. Once deployed, we see the pendulum successfully swing up and balance in the upright position. A quick disturbance test also shows that the controller is robust to external disturbances. In this video, we showed how you can guide an AI agent through the control system development workflow, verifying key stages, identifying and resolving issues along the way, and ultimately deploying to embedded hardware. If you're interested in testing a similar workflow for your own control application, check out the resources below to connect your AI agent to MATLAB and get started.